So today we're going to talk about power functions and variation, which is something maybe direct variation, inverse variation. That's maybe something you've seen before, and we'll tie that in with power functions. So this right here is our power function formula. And if you look at it, it's very, very basic. There's not much going on here. There's no addition, subtraction. This is it right here. And so if you think about the other functions that we've talked about and how all the transformations happen, you could probably imagine that this k value is, in every textbook uses different variables. This particular book uses a k. That's really like that old a value on a parabola. It's going to be your vertical stretch and your reflection, and then you have some variable, and it's going to be raised to some power. All right, so what I want you to think about, a power function is pretty versatile. It actually, several of the functions on our toolkit are power functions. The parent graphs are power functions. So if you consider, and we did this in class with Desmos where you could change this a value. But if you think about it, if that a value was a 1, really this would just be an x to the first. So this would be some sort of a linear function. It would just do that, okay? But if your a was a 2, well, then it would be a quadratic, so it would be a parabola. So a power function can really just be one of these parent graphs. If it was a 3, it could be a cubic. If it was a 4, it'd be a quartic. All right, and then we went the other direction. What if it was less than 1? What if it was a 1/2? Do you remember what an x to the 1/2 is? Well, an x to the 1/2 is really the same as a square root of x. So this power function could be a square root function as well, if it was a fractional. And then think about what if that a value was negative, if it was like a -1. Okay, well, that's equivalent to 1 over x. So now a power function can also be a rational, which does this thing. So if your a value happens to be negative. So thinking through all of that, and you have a little part on your homework where you have to sort of match a graph to one of these power functions. And so you've got to know your parent graphs from your toolkit pretty well, so that when you look at this right here, you can see that, all right, what I'm really looking at is this is an x cubed. Okay, I know what a cubic looks like. But then it also has this -3 for a coefficient, which is going to reflect it. So I know that in general, this graph is going to look something like this right here. It's the cubic that's been reflected. It's got a little vertical stretch on it. Okay, let's look at the next one. On this one, we have a y equals 4x to the 1/3. And I'm looking at the power. The power is a 1/3. All right, that's fractional. That's going to be like this scenario. It happens to be a 1/3 instead of a 1/2. Okay, so instead of a square root, that means it's a cube root. Now, we haven't really graphed cube roots before, but ultimately it looks something like this. It actually is okay on a cube root to be negative, have a negative radicand. So it actually does have a piece over here on the left side, whereas square root functions only start at the origin and go right. So this is what a cube root would look like. All right, last one. Now you have a -2 for a power. All right, so that leads me to thinking it's kind of like a rational, except that it's a 2, not a 1. Do you remember what happens when you end up with a 1 over x squared instead of x? All right, so hopefully you remember that the squared pops both of these little hyperbola pieces, is what that really is, or branches of a hyperbola. It pops it up, so it would look like this. Now, if the 2 is negative, then it would reflect down from there. It's not, so don't get thinking about the negative being a reflection. That negative is popping it to the denominator. All right, so now knowing that a power function can really represent several different types of our toolkit parent functions, I'm going to give you a table here, and let's see if we can figure out what kind of function it is. So using this parent graph right here, this is sort of like what we did with parabolas. I'm giving you some ordered pairs, and we're going to plug them in and see what happens. And when I say we're going to plug them in, I really don't need this many. I'm only going to pick I guess I'm going to start with this because it seems like the simplest, right? If I put in a 1 for x and a 2 for y, my goal is to figure out this k and a value. So I'm going to put in a 2 for the y. I'm going to put a 1 in for the x and take it to the a power. Now, I did give you 4 ordered pairs. It is going to be important that I give you the ordered pair that has an x value of 1 to do this right here. If you take a 1 to the a power, it doesn't matter if a is 2 or 7 or 33 or negative 15. 1 to any power is always 1. So what this is allowing me to do is to ignore the a for a minute so that I can figure out what k is. All right, so k is going to be equal to 2. Once I know what k is, now I'm going to start over. I'm going to do it again with a different point, and I have 3 more options. I'm just going to go to the next one. I'm going to use the 216. Put 16 in for the y. I now know that k is 2, so I'm going to put a 2 in for the k. The x is going to be the 2 raised to some power. And then I'm going to solve for that power. So divide by 2. Remember your order of operations. You can't multiply those 2's because the second 2 is getting raised to a power. All right, now we would actually have to do a logarithm to solve this, but we haven't really, I know you've done logarithms. We haven't done them in here yet. I'm going to probably keep this simple enough. You probably can just do that in your head. Ideally, you can see that a would need to equal 3 in this case. All right, so then your goal is to write the function. So now that you know k and a, we'll come back and let's write that function. It's going to be 2x to the third. So this particular power function is actually a cubic. All right, so that was the gist of power functions. Now what we're going to focus on are some types of power functions that you probably have seen before. It's called direct and inverse variation. And direct variation has the situation where you have some sort of a constant here. Again, it's a very basic equation. There's no addition, subtraction. It's just a y equals k times some x value. The way that we read this is we say that y varies directly as x. And to vary directly, then there's this k value sort of dictating what it varies by. But in general, if I guess we typically think of it in real world situations as x increases, so does y. Let's look at this. Second option is inverse variation. Y varies inversely as x. So, and then k is going to be some number, some constant. Inversely would imply that as x gets bigger, the y is actually going to get smaller. And that would make sense because x is in your denominator. So the bigger that gets, if it's a tenth, if that's a 10 or a 100, 1,000, yeah, that's getting smaller and smaller and smaller. So inverse variation, they kind of do the opposite. And then we have this one called joint variation. It's a little bit different because you have extra variables involved. Z actually varies jointly as x and y. So it looks like it's direct variation, but it actually is varying by 2 different factors that play a part in what happens to z. Okay, so let's look at some of these problems. So let's start off working with some variation statements so you know how to set these formulas up. So I've actually given you a couple formulas first of all, and what I want to do is go ahead and write what we call a variation statement that sort of explains what's going on in this formula. Hopefully you look at this first one and you can see, oh, that's the area of a circle. So looking at it, I can see that I'm taking pi and I'm multiplying it by my variable here. I'm multiplying it by r squared. So multiplication implies direct variation. And so the pi here is really my k value because pi is a constant. It doesn't change. And sometimes it'll be a number like you think of a 3 or something, but in this case, it's pi. So I'm going to write my variation statement, and I'm going to say that the area of a circle varies, and we decided it's going to be directly, so it varies directly. Some other phrases that you'll see, sometimes it'll say it varies proportionally. That's the same as direct variation. It might say that it is proportional. Okay, another way of saying varies directly. Directly has some options. If it's going to be inverse variation, it will say inverse. If it's going to be joint, it will say joint. So if it says some other stuff, then we go with direct. All right, area of a circle varies directly as the square of the radius, not just the radius, but the square of it. And usually textbooks will write the square of the radius versus writing radius squared. I don't care. Either way is fine. Now, it is also important to indicate what else is going on in this formula. And so, again, textbooks will write with a constant of variation, like this, with a constant of variation of pi. Now, this gets a little bit wordy. We're already kind of writing a bunch. I'm going to let you do a shortcut here. Instead of saying with a constant of variation of pi or equal to pi, I let you just in parentheses, after you've written this sentence, just tell me in parentheses what k is. And in this case, k is pi. Now I'm going to write k equals pi, but I might still say, oh, and the constant of variation is pi. But if you're writing it, I'll let you do that shortcut. All right, so let's move on to the second one. This formula, maybe we don't know what it is. So what do you do then? Well, if you don't really know exactly what this is standing for, then I let you go ahead and just write the letters, and they don't really have a formula that you're familiar with. So I would just say in this case, F varies, and then you look at it and you try to decide, is it going to be direct or inverse? Looking at this, I have a k on the top, and the variable d squared is in the bottom. All right, so if I'm dividing, that's inverse, or I'm sorry, inverse, yeah. F varies inversely with the square of d. Don't get that confused with the square root of d. It's the square of d. There is a difference. And then in this case, it's kind of weird because there isn't a number in it. So my constant of variation is really just k. So that's kind of weird, but I'm just going to write k is equal to k. That's what my constant of variation is. All right, so in these scenarios, I'm giving you the formula, you're writing the variation statement. Now let's go the other way. What if I give you the variation statement? Can you write the formula? I'm going to have you go ahead and just do this first one for me. Okay, hopefully you have. The period, so I'll call that P, of a pendulum varies directly, so equals K times the square root of its length. Square root of its length. Usually we'll do a cursive L for that, but you could do a capital L. Don't really want to put just something that looks like a 1. Okay, next one's a little bit trickier because I have multiple things going on, which is okay. It says force is directly proportional to the mass and inversely proportional to the square of the radius. Right? I don't want two separate formulas. All of this has to tie into the same formula. So I have F equals directly proportional, so that's K times the mass. And it's inversely proportional, so I'll turn it now into a fraction, to the square of the radius, to r squared. And that's my formula. All right, so understanding how to go back and forth between those, because I'm going to give you some word problems that you have to actually then write the formula for. I'm going to start with a generic one here that doesn't have really much meaning, and then we're going to jump into some applications that actually mean something to us. All right, now, when you are doing these problems, they're pretty much like there's 3 steps involved. Like almost every time, there's 3 steps involved. And even if it doesn't like break it down, it's all kind of a sentence. I've underlined the key parts that they're asking you to do. Those are the 3 steps. I need to see all 3 of those because that's going to be worth 3 points to you. Okay, so then what I've got is, I'm going to just start over here with a number 1. Here's your first step always. Determine the constant of proportionality. Okay, so what they're telling me is I have to figure out what K equals. That's what they want first. if x is inversely proportional to the square of y. All right, I think I can write that. X is inversely proportional, so it's going to be k over the square of y. All right, so that's going to be my formula. But that's really not my answer because my answer was to find k. It does tell me that when y is 7, x is 3. All right, well, that's enough for me to figure out k then. So I'm going to keep going. This is still step 1. All right, multiply both sides times 49. And I've got k to equal 147. All right, that's the answer to the first part. It says, then write the mathematical model. All right, I sort of already did that, except that this is not all that helpful of a model until I know what k is. So when they say write the model, they want you to write it with your k value in there. So that's step 2. X equals, and instead of a k, we put the 147 over y squared. That is called your mathematical model. Step 3 is you then using your model to figure something out. So in this case, we want to use our model to find x if y is 13. So I just put in 13 for the y. And then I'll just calculate that. I already did that ahead of time so that I would have my answer. And x is equal to 0.870. Okay, so now let's take that idea. And so again, I can't emphasize it enough. I need 3 steps of work on those. They're worth 3 points. Next thing then, let's go apply this to something a little bit more, has more meaning. Okay, let's do this. Why don't you first just read this? I don't really need to read it out loud to you. Take a moment. I'm just gonna sit here. You don't even have to pause the video. Just go read this. All right, so moving on to the next slide, which is a continuation of that. It says write an equation of variation. They just jumped right in and asked for the variation. There's 2 steps that get me there, though. I have to start off and I have to figure out what k is. And they did give me information to figure out k. Once I know k, then I'll write the equation, but it's 2 steps to get there. All right, so they said that the sales vary directly, so that's k times their advertising expense. So that sort of makes sense. As you spend more in advertising, you should be making more sales. But it varies inversely as the price of the skates, which also should make sense to you. As those get more expensive, as you charge more, your sales probably go down a little bit. So now then they give us a whole bunch of numbers. So those numbers are going to help us figure out K. I'm going to put, it said they have sales of 12,000. Advertising of 60,000, and they're charging $80 for the skates. Okay, so to solve for k, I'm going to take both sides times 80, get rid of the fraction, and then I'm going to come back and I'm going to divide by 60,000. If I do that, I end up with k coming out nice. This is convenient, is 16. Once I know k, I'm actually ready to write that model or that equation of variation. So it goes S equals 16 times A over P. That's your model or your equation of variation. Now let's use it. Determine monthly sales if the amount of advertising is increased to $70,000. Okay, this is a classic analyst position at some company, or this is what mathematicians do. They go become analysts someplace. You're in charge of deciding if, hey, what if we advertise a little bit more? Would we make more money if we did that? So let's find out. The sales last time, recall, were 12,000. So we're going to see what happens if I change that. So I'm not going to put the 12,000 in this time. I just want to know, what are the sales going to be? My K is 16. The advertising, we're going to jump up $70,000. And we're still keeping the same price of $80. If you plug that all into your calculator, you're going to find that your sales end up being 14,000 instead of 12,000. All right, so that seems good, right? We sold 2,000 more pairs of skates. Great. But I'm not sure that that really answers the question, is it worth it or not? Should we be, I mean, is that enough more sales to justify the extra expense in advertising? So then I have to go to the next level and kind of think about, okay, so I'm selling 14,000 pairs of skates. Skating must have come back. I don't know. That seems like a lot of skates, but okay. So 14,000 skates, and you're charging $80 for every pair. And really, I say 14,000, it's really that you have sold 2,000 more than you were previously. We were selling 12,000, now we're selling 14,000. We've got 2,000 more pairs we sold times the $80 that we're selling them all for. So what that means money-wise is that you're going to make $160,000 more for an investment of 10,000 extra dollars in advertising. Seems like a pretty good deal. I'd do it. All right, I got one more for us here. This one does not have any numbers in it. This is just understanding sort of what happens. This is kind of a nice engineering kind of problem. It says here that the maximum load that can safely be supported on a horizontal beam varies jointly as the width and the square of its depth. Okay, so it's jointly, meaning it's multiplied. That sort of makes sense. If you make it wider and you make it deeper and it's more stout, that the maximum load, as those get bigger, so will the load. It'll be able to hold more. But it's going to vary inversely as the length of the beam. As that beam gets longer, it starts to sag in the middle. It's not able to hold as much. So that's why it's inverse. Okay, it says write a mathematical model for the above statement. Can do. Here we go. The load, which it's the maximum load, so that's M, is equal to K, and we're doing joint variation. So K times W, the width, and the square of its depth, D squared. But it varies inversely, so we turn that into a fraction, as the length. So we put L underneath here. That's sort of our formula. Now, what we're really doing is it says, determine how each change affects the beam's maximum load. I'm not giving you numbers. We're just going to see what's going to happen to your formula. This is the standard formula right here, what we have. What changes on that as we do something? So this says, what if I tripled the width? What's going to happen to the maximum load if I triple the width? Well, here's what that would look like. K is still there. I don't really know what to do with the K, but the width is not W. The width is now 3W. Everything else stays the same. So ultimately, what I can do here is I can factor that 3 out in front, and then I'll have my KWD squared over L. Remember that that's sort of what the standard is. That's what it was. But now your maximum load is 3 times what it used to be. Okay, so that's what they're asking. It says write your answer in terms of M. Okay, well, I guess that would be 3M then. Or I kind of like it as a sentence, that it would be 3 times stronger, could hold more. Okay, so I'm just keep doing the same thing. I'm just going to change different things. All right, so this time I'm going to double the depth. All right, that's making it stronger. I know it's going to make it stronger because it's more stout the deeper it gets. How much stronger? So when you look at this is a little bit different scenario because your width is staying the same, but now instead of it being a D, it's going to be a 2D squared. this 2d squared is going to actually turn into a 4d squared. So if I factor all the number stuff out, you can see here that now my maximum load is 4 times what it was originally. All right, I'm going to do one more, then I'm going to turn you loose on the last one. So this time what I'm going to do is I'm going to half the length. I'm going to make it shorter. Again, just thinking common sense, I feel like that's going to make it stronger because it won't bow as much in the middle. But that seems weird because I'm putting in a 1/2. How is that going to work? Instead of an L, it's now a 1/2 L. But remember that dividing by 1/2 is really, I can just pop that up. It's the same as multiplying by a 2. So dividing by 1/2, the same as multiplying by 2. Didn't mean to cross that off. So this times 2 is what I would be factoring out front on this. And then I would have the KWD squared over L. So actually, if I half the length, then my load is going to end up being twice as much as what it used to be. All right, now it's your turn. You try the next one. You're going to do 2 things. You're going to half the width. Okay, that's not going to help. You're going to double the length. That's not going to help. All right, let's see how bad off we're going to be in the end on that one. So see what you can do with D. Go ahead and pause the video. Come back when you're done. All right, so this is what I got. I put in my numbers, and then with this 2 in the denominator, I brought it up. Dividing by 2 is the same as multiplying by a 1/2. So instead of doing that, I put it up here. I've got a 1/2 times another 1/2. That's going to be a 1/4. My maximum load is 1/4 of what it used to be. All right, kind of fun, huh? All right. Your homework should be on a worksheet. Good luck.